Hello everyone. In this video, I will derive a relationship between a statistical mechanics and thermodynamics. So, in order to derive the relationship between them, here I had assumed two independent systems, say system 1 and system 2. So, these two independent systems, I have written it that in system 1 it has an entropy S1 and in system 2 it has an entropy S2, and corresponding to their entropy they had their microstates. The numbers, say microstates, are like number of the atoms or number of the particles inside it to be omega 2 for this entropy and omega 1 for this entropy. Now it is quite obvious to us that if a system has a higher entropy, then it will obviously have larger number of particles inside it, or we can simply say larger number of microstates inside it. So, and similarly, if a system has lower entropy, then obviously it will have a less number of particles or lower number of microstates inside it. So here we can see that this entropy is somewhat related to the microstate, and here we are assuming that it is related by this function, say f. Entropy is related to the microstate with a function, say f. Now if we try to, now after this, if we proceed to our derivation part, we are assuming that we are removing this thing that is separating these two systems from each other. After the removal of this block, or say after this slab, these two systems will mix with each other, and entropy being an extensive property, the overall entropy of the system can be written as S1 plus S2, because entropy is an extensive property. So overall entropy will be S1 plus S2, and here if we put S1 in our first equation, we get f of S1, which is equals to f of omega 1, and similarly S2 corresponds to f of S2, which is equals to f of omega 2. Now after mixing, the total number of microstates in the system will be not it will not be omega 1 plus omega 2, rather the total microstate inside the system will be omega 1 times omega 2. This is because corresponding to each microstate in system 1 there will be a microstate in system 2. So because of that reason, the overall or overall microstate in the system after the mixing of the two independent system will be omega 1 times omega 2. So corresponding to this, what we can write is f of omega 1 plus f of omega 2 is somewhat like f of omega 1 times f of omega 2. This we can write after putting the values in the function that we have assumed earlier. So now if we partially derivate this function with respect to omega 1 and then with respect to omega 2, we will get like, first differentiating with respect to omega 1 partially, f dash omega 1 plus 0 equals to omega 2 times f dash omega 1 into omega 2. Say this is our equation 1, and now if we partially derivate with respect to omega 2, we get f dash omega 2 plus 0 equals to omega 1 times f dash omega 1 into omega 2. This is our equation 2, say. Now if we multiply our equation 1 with say omega 1 and our equation 2 with omega 2, we get f dash omega 1 is equals to omega 1 omega 2 f dash omega 1 omega 2. Here also we will get omega 1, and in the equation 2 we get omega 2 f dash omega 2 is equals to omega 1 times omega 2 f dash omega 1 omega 2. So we are seeing that this side the RHS of both the equations are equal. So equating them, the equation that we will get like omega 1 times f dash omega 1 equals to omega 2 times f dash omega 2 equals to omega 1 omega 2 f dash omega 1 omega 2. This is the equation that we are getting after partially derivating the equation that we have got earlier. So here we can see that this quantity is totally is a function of omega 1, and this quantity is totally a function of omega 2, and both this quantity are being equal to a particular value. So this will obviously be a constant value, because for a constant value only these function which is purely independent of omega 1 and omega 2 will become equal to particular value. So this will be a constant. So from here, if we generalize our equation, we can write that omega times f dash omega is a constant, where omega is a representative of all the microstates, because here we are seeing that for a particular microstate omega 1 we are getting a value constant, for a particular microstate omega 2 we are getting a value constant. So we can generalize it writing it as omega, which is a representative of the microstates. So omega into omega dash f dash omega is a constant. So from this we can write omega into d of f of omega by d of omega is a constant. So we can write from this. So further taking it ahead, d of f of omega is equals to k times d omega by omega. So we can write this. Now further going ahead, we can write it as, if we integrate it, basically now we are going to integrate both the sides. So this is f of omega, which is equals to k times ln of omega plus c. So we know that 1 by omega integration is ln omega. I had written it directly. So from this we had earlier assumed, from the starting of the video I had assumed that entropy is a function of omega. So at that time I had written it to be entropy is a function of microstate. I had written it to be something like this. So we can now replace this f of omega with this entropy. So entropy is our k times ln of omega plus c. That c comes out to be 0 eventually after we put certain conditions, certain initializations. That we put, the value of c comes out to be 0. So finally the equation that we are arriving is at entropy is equals to k, and this k comes out to be Boltzmann constant ln of omega. So this is the relation that we were trying to derive from the starting of the video, where where s is the entropy of the system, omega is the number of microstates in the system, this kb is Boltzmann constant. So this is a thermodynamical quantity, and this omega is a statistical quantity. So here this is the relationship between thermodynamics and statistical mechanics. I hope that you all understood it. Thank you for watching it.